What we are going to do today is to solve two different problems. I suggest that you look at them carefully because the final is going to be very similar. I'm not suggesting that the final will have all of these questions, but some of these questions for a different, with some different numbers, obviously, will show up in the final. So I will share my screen. Okay. And I have two problems that I'm solving here. One, so I said, not all of this is going to be on the final. All right. So you just so you know, some of these questions will be on the final. But if you solve these two problems and you know how to find the solution, then I think you're going to do well, because it is from these two problems that I will incorporate questions in the final. So, and I will do as simple as possible, because I would like to see how much you understand and not, how extensive calculations you make. This is not what I had in mind. Let me see, admit some of the students. Okay. All right. So the, let me see. I think there are students who are just, unfortunately, in these office hours, I had an admit. So, all right. I don't think anybody's waiting. Okay, so the first one is on filter design. And you will see here, I will read the problem carefully. So that's the number one you have to do, because I think many of you start solving something without having read the problem carefully. And a lot of times you're solving for the wrong thing. So even if your solution may be accurate, it's a solution for a different problem. And you cannot get many points, out of a solution for a different problem. Or if anything else, in most cases, that's a rare case, but in most cases, you get confused and you don't solve the problem. That might be much simpler. Okay, so in this case, I want you to design a stepped impedance low pass filter with a cutoff at 4 gigahertz and an R0 or R0 at 50 ohms. R0 is usually the impedance of the source and the impedance of the load, if those two are identical. So 50 ohm, it's a reference impedance. The R0 is a reference impedance, 50 ohms, always. Here, I ask you to use an N equals 2 stage design. I specify how many sections I would like to have in this. And also, I want you to design a maximally flat filter. So I say, assume a maximally flat filter performance, okay? And then, having given you this, I would like you to find the rejection at 8 gigahertz before you do anything else. And then I want you to identify the impedance and length of the filter sections, assuming an ideal transmission line model with a low impedance of 10 ohms possible and a high impedance of 120 ohms. Okay. So I specify the low and I specify the high. And the other thing, which is interesting, I also tell you to do it in an ideal transmission line. All right. To minimize your calculations. Now, so we start with the two figures. One is a table that says element values for table 8.3. And from there, you find the n equals 0. This is what I asked you. And then you see for all of these, the last stage, which is the n plus 3 plus 1, so 3 in this case, is always 1. All right, you see the values of all of the g n plus 1. So for a 2-stage, when n equals 2, you have G1, G2, and G3, and G3 is 1. So with n equals 2, now I go here. I gave you that the cutoff frequency is 4 gigahertz here. And then I'm asking you to find the rejection at 8. So the ratio of these two, omega over omega sub c, is 2. And so 2 minus 1 gives 1.
Dr. Katehi?
For
this kind of questions, if the intersection is not exactly on an n curve, do we round or always seal?
What do you mean an n curve?
For example, yeah, like the
if I have given you the rejection, you mean?
No, the n curve is just the figure 8.26.
There's never n equals n, point something.
Figure 8.26, sorry.
The 8, yes, okay, so that figure, yes.
And that figure, then once we find the value of omega minus omega c minus 1,
yeah.
Also the dB, but it's not exactly on the curve of n. Do we round or seal the value of n?
So here, if I give you the rejection, in this case, make sure you understand that I don't give you the rejection, I give you the stage. All right, so I tell you n equals 2. So in this case, I give you n equals 2. And so you try to approximate it. Obviously, I made an approximation myself, all right? It's probably the best I could do. Minus 13 dBs, I said, so probably it's an approximation. Now, if I tell you, for example, I want a rejection, which is 15 dBs. So usually attenuation includes the negative. That's why I put minus, but rejection or attenuation in reality is a double thing, all right? So minus n rejection is you use it twice, but in any case, you see positive values because the attenuation it implies is lower. It's minus. In any case, if I tell you 15, and 15 is here, oops. Let me do this. If I tell you 15 and 15 is here, there, and I draw a line here. Hope it's going to become a line. Okay. In this case, you're going to go for n equals 3. It's better to over design than under. It's better to have more rejection than less.
Okay. What if like the rejection is like 14? Then that's when it is rounded.
The rule is over design than under.
Okay, so it's always to seal.
Yes, exactly. That's what you mean. Yeah. Yes. Okay. In any case, that's for so in this case, you answer the first question by using this graph. Then what I ask you to do in the second is to identify the impedance and length of the filter section. So I'm asking you practically to design the filter and then assume it's an ideal transmission line. And then that the lowest impedance you can use is 10. The highest impedance you can use is 120. And then I want you for this ideal transmission line to find the lengths. And usually we find the lengths in terms of a wavelength, all right? So how do we solve this problem? We start with a regular solution. We go to the low pass prototype. This has 2 stages. So G0 is R0, G3, which is the load, is R0, 1 in this case. G1 is C. I put the capacitance first because I have the Thevenin equivalent for the source. So it's a series source oscillator and a series Thevenin equivalent resistance, R0. So I put a capacitor first, as the book says.
Professor?
Yes.
Are we just supposed to assume that it's a voltage source that we're going to use? Because I didn't see if it said a voltage source or a current source in the problem.
It's always, I mean, unless I tell you you're going to use a voltage source.
Okay, thank you.
Unless I tell you. If there is other than that, normally we say.
So
Okay?
the default consideration is voltage source and
Yes.
it's shunt capacitor.
Yes, exactly.
But if it's given with a current source, then it is a series
inductor first. Yes. Okay. So now I don't give anything. So the default is the voltage source, as you said. And then, so C is G1, L is G2. G1 and G2 have the same numbers. All right, same value. So now there are 2 transformations I do only because I told you to be a low pass filter. So I don't want to do low pass to band pass. No, the only 2 transformations to go from a low pass prototype to a low pass filter is the impedance scaling and the frequency scaling. And that's how they look. So then if you plug in for the numbers here, then you find, and be careful of the units, all right? So you find C to be 1.12 picofarads, and you find L to be 2.81 nanohenries. And so in circuit form, in lumped element form, this is how it looks. Okay? Any questions so far?
Professor, if we're using MATLAB during the exam, should we like provide code that we used to do this instead of doing it like on the paper?
Now, let me just tell you, I don't want to read code. All right, I don't want to have to go and read code. You may want to use MATLAB, but I want you to write on paper what you found. Because I've noticed from the last that you just put the code there. No, it's difficult for me to read somebody else's code. And then I have to go and check the code line by line. I'm not going to do that. Use the code to get your data, but I want you not necessarily to do the calculations like I did on paper, but I want you to write things as I do. See? I don't want you to return a code to me at the end of this. I want this kind of presentation.
Analog professors never like code, unlike digital courses.
No, well, yeah, because I'm not checking I don't want to check your code if it's correct or not. I'm not, digital professors like code. Maybe that's because that's the only thing they know. Sorry, not really. I mean, I don't know. I think unless I give you directions on how to write the code, it's going to be difficult to check everybody else's code because every person writes a code in a different way. And then I will have to go and check everybody's code because I will do 2 things. Either I will check the last values, and if they're incorrect, I'm going to give you a bad grade. Or if you don't write it like that, you're not going to get partial credit. That's the problem, all right? I want to see how you're thinking about the design. And in the analog, yes, I mean, of course, knowing how to write code is good and very helpful, but you're not getting a grade for the code. I want you, however, to use any tools you have available to you to make it easier, but also try to help me help you to give you points in your design. Okay, is that clear? All right. So this one now, what do we do next? I asked you to find the impedances, which I gave really. So when somebody tells you to design a filter, which is a, say, low pass filter in this case, and they give you the lowest impedance you can use and the highest impedance, and they tell you a stepped filter. So you know you have to use sections of lines, obviously, to do it. If they say stepped, they don't say use stubs. If they say stepped, it means sections of lines. If I wanted you to use stubs, I would have told you, all right? Usually I will do that if I want you to use a stub. So stepped, here lines. If I tell you the lowest impedance you can use and the highest, that implies that that's how low you can go and that's how high you can go. And usually for a stepped impedance filter, you use the lowest you can go for a capacitor, the lowest characteristic impedance you can use to realize the capacitor, and you use the highest impedance you can use to realize the inductor. Now here, I use the microstrip because visually helps you to see the stepped, all right, the stepping, or they called it stepped impedance because you have step changes in the characteristic impedance, and in the microstrip is visually also is visible, I should say, because you change the width of the line. And what did we say? We said that a low impedance, do you remember, before I go to that, let me ask you this question. If I had a section of line like this, let me write here, a section of line like this, okay? And then the line has L, the inductance per unit length, the equivalent inductance per unit length, and C to be the equivalent capacitance per unit length. Do you remember how much is the characteristic impedance of this line?
Square root of L over C.
Yes, it's L over C. And do you remember what we said? That a line that has low characteristic impedance normally has what? Of what is the characteristic between L and C per unit length for this line? That has
Higher inductance.
high what?
Inductance.
No,
High
I said
capacitance.
low, yes.
Oh,
I said
low.
low,
is-
I said, yeah. I said low characteristic impedance, it means high capacitance. Because C is in the denominator, right, inside the square root. So when you have to realize a capacitance, a shunt capacitance, obviously, with a section of line, you are looking at the lowest possible characteristic impedance of a line that you can realize, and you use that. And why do I use the lowest possible impedance? Because the lowest possible impedance from this expression here is going to also give me the lowest possible length. All right? Otherwise, if you try to materialize a capacitance from a line that has not very low impedance, then you get very long lengths of line, and we know that these formulas do not apply for very long lengths of line. They apply only for short lengths of line. So this is what I'm using here, and I'm looking for the lowest they gave me, which is 10 ohms. And I plug in the values here, and I get a length of line for this impedance for 10 ohms to be 0.045 of a wavelength. That's very low. So I know that I'm accurate in this calculation that I've done. So if I use a line that has 10 ohms characteristic impedance and then has this length that I found here, then this line is going to be equivalent to capacitor. Now, in parallel with that, and only for, just to remember, if it is microstrip, a low characteristic impedance line has a wider, you remember, conductor. And that's why it looks like this in microstrip. It looks like a section of line that has a wider conductor from, of course, the 50 ohm lines that feed it, because you have one 50 ohm line here and another 50 ohm line there. But this is much lower characteristic impedance, 10 ohms. So it's much wider W. Okay, then I found that length. Now, I go to the inductive section, to the inductor. I want to materialize the series inductor that I have.
Excuse me,
Yes.
Professor. So how do we determine the ZL, the low in the capacitive region?
I gave it to you. So
Oh.
I said the lowest was 10 ohms in the beginning, in the problem. Here.
Ah.
All right. So I gave it to you. That's why it is very important to read it carefully when I give you the problem.
Okay.
Okay. Of course, I have to give it to you because I'm not asking you to do anything, any particular line. So how would you know whether you can materialize 10 ohms if I don't tell you? If I ask you to do an ideal transmission line, anything is possible in an ideal transmission line, see? But it's ideal. So in reality, not anything is possible. I mean, if you have an ideal transmission line, you can say ideally, you can have an impedance which is 1 ohm. Well, yeah, in an ideal world, you can find 1 ohm, but in real world, there is no impedance that has 1 ohm characteristic impedance. There's no line that has 1 ohm characteristic impedance, all right? So I gave this to you, as I gave you also the high impedance. So now we go to the inductance, to the inductive section. And now, for the same reason, since Z naught here is square root of L over C, then we know that a high characteristic impedance will give you a high inductance, or a high inductance per unit length in a line will give you a high impedance. So to materialize my inductor, I need a high impedance section, because that's from here, if I use a high impedance section here, it's going to give for me the lowest possible length of line. And I need very low lengths of line because this is the condition under which I got the simplified expressions. Okay, so then I'm using this formula. I put the L, I calculate it from the filter that I designed. I put Z sub H to be 120 ohms. I put omega sub C. I made the calculations and I found that for this section of line, the length is 0.093 of the wavelength, which is very small, and therefore I am confident that my calculations give me an accurate value, okay? And so visually, even if, you will see that sometimes in some books, but even if I did it for your, when we call stepped impedance, stepping in the characteristic impedance, usually that's how we show in an ideal transmission line form, a high impedance, the green, a low impedance, the red. So this is the high impedance section, and this is the low impedance section. And we have found the two lengths. So that's how you do this filter. Any questions so far?
Professor, I noticed that the length of the inductance section is about 2 times as big as the length of the capacitance section. Is that kind of a range that we should shoot for? Like, is that a way we can verify if we're doing calculations?
No, not necessarily. It depends so much on the value of L and C you get.
Okay.
It just happened here. All right.
Right.
The values of L and C and the values of low Z or high Z It just happened that it happened like this, but it's not necessarily true that it's going to happen all the time.
Okay.
You just need them to be very small. So you need to have a zero in front. See, you need to have a 0.0 something. So you know, you need to have them at least to be smaller than a tenth of a wavelength. See? To say that they are small. That's what you need.
Okay. Thank you.
Sure. Any other questions about that?
So you said Z naught equals square root of L over C. Then what about if there are more stages? Then there are more L's and C's.
Then you follow the same thing. You will always use the same law and the same high impedance, but the lengths will be different. In a stepped, if you have more L's and more C's, when you do the translation of, say, all of the C's will be different, obviously, all right? They're not all of them going to be the same. They're going to be different, but your low impedance will always be the same. It's just the lengths will be different. Get this?
What about the intrinsic impedance?
What?
Intrinsic impedance.
Intrinsic.
Z naught.
Oh, yeah, all of the capacitive sections, we have the same low impedance, which is 10 ohms. And all of the inductive sections.
No, not Z low, Z naught, not Z low.
Z naught is only on the input and on the output, and it's 50 ohms.
So do we use that C or the C we found?
What Z?
C, capacitance.
Oh, no, the C you found from the design. I don't understand what is confusing there.
Because the green thing, Z naught equals square root of L over C.
Yeah, this is what any characteristic impedance. This is not your L for the filter and not your C for the filter. This is the L per unit length of the line and the C per unit length of the line.
So that doesn't make a difference to the problem.
No, it only makes a difference for you to remember that if you want to materialize a capacitance, then you always go to a low impedance. And if you want to materialize an inductance, you always go to a high impedance. This is what I put them there. Okay. And I will eliminate them just in case I just did it here. I'll get rid of them just in case it confuses you. But so you remember. Any other questions?
I do. So we don't going to measure, calculate the width W for each section.
I did not ask for it. And since I asked you to do an ideal transmission line, ideal transmission lines do not have widths.
I see. Okay.
Okay. Any other questions? Okay. Now we go to a LNA design. And some steps I have left to do them here slowly because I know that some of you will need that review again. Okay. I will give you, as I said, a unilateral amplifier to simplify things. Because I know that some of you are still confused about stability, about how to draw the circles, and about how to draw both the gain and the noise circles. So I would like to take time today and go through this again. But you learn, follow this solution, and then you need to know how to solve any of these questions. I'm not going to give you all of them because doing all of them is going to be, it's going to take you time, obviously. But I may give you any one of them Or I may give you some, if I take one question, I may give you something and then ask you to finish the steps. All right. So I will make sure that you will have, it's only 2.5 hours practically. So I know it takes time. If it takes time for me to put all of this together, it's going to take even a lot more time for you. So I'm not going to give you all of this, but this is what you need to know. All right. These questions, how to calculate the so I will read it carefully for you. What do I give you here? This is, I give you a BJT that has been measured. Usually we always give the bias, even if there is nothing for you to do about the bias, all right? So we always give it because that's the right reference. And then they give you frequency, is important, and the reference impedance of the system. It's always a 50 ohm, always a 50 ohm. If for some reason they don't give it to you, then you assume 50 ohms, all right? But say that I'm assuming 50 ohms in this one. So people, if it's not there, for here, I gave it to you. And what do I give you now for this BJT? At that single one frequency, because here is what some of you did in the last problem. You get scattering parameters at one frequency. You get scattering parameters at one frequency. And then you plot them over, I don't know how many frequencies. Well, it's not correct. The scattering, you remember how when you get all of these pages and pages of specs for a transistor, you see that every frequency you have different scattering parameters. So you cannot use the same scattering parameters and then design the transistor at one frequency and then say the frequency is 10 gigahertz and you go and plot from 1 to 100. Who knows what crazy things you're going to find out in there. The maximum you can do, if you design something around 10 gigahertz to go from like 9 to 11, or if you are around 1 gigahertz to go from 950 to like 1050, all right? That's why some of you saw some crazy stuff because you were plotting the whole spectrum. No, you cannot do that. All right. So here it's only the scattering parameters at 1 gigahertz only. Then you have, I give you S11, magnitude and phase. S12 is 0. I give you S21. I give you S22. And then what else do I give you? F minimum, which I measured for that transistor, it cannot go below 4 dBs. Gamma optimum, and R sub n, which is the noise impedance in ohms, is 4.5 ohms. Okay? That's what I gave you. All right. So for that, we now have I asked you to calculate. Now I have to tell you, first of all, this is not a real transistor. I had to put S12 equals 0 to make things simpler for you. So don't believe this is a real transistor. I just made up I just changed, as I said, it had very small S12, I made it 0. And then I also changed the F minimum to make it work. So now I first of all want you to calculate the optimum terminations for a maximum gain. First of all, you start. What happens when S12 equals 0? What happens when S12 for a transistor equals 0?
Gamma in equal S11.
What is it?
Gamma in
How do we call this transistor?
It's unilateral.
unilateral.
Unilateral, LND amplifier, obviously, all right? What does that really mean before we go to equations? What does this mean that a transistor is unilateral?
There's no feedback, and so the
Yes.
matching networks will be distinct. They don't affect each other.
Yes, so the input and output matching networks don't see each other, right? They don't. So you can design them independently. And that means that the gain of every section, which is the input matching network, is a section in the amplifier, the transistor is a section, the output matching network is a section. The input section and the output section act independently. That's what it means. So practically there's no feedback, because if there is feedback, then they see each other. Okay. Now, what happens when a transistor is unilateral? What happens in terms of stability? And especially this transistor. That the transistor is unilateral and all of the S11s, with the exception as to S11 and S22, are less than 1. What happens to that? Magnitude, I mean.
Transition.
Is unconditionally stable. Okay? Do you remember that?
Yes.
Yes. Okay. So when a transistor is unilateral, and the S11 and S22 magnitude is less than 1, and you remember what I said? That most of the time, the transistors you're going to be asked to solve will be the magnitude of S11 and S22 will be less than 1 in most cases. So you don't worry that I'm going to give you something that is bigger than 1 for these two scattering parameters, all right? I'm not going to do that. But you need to remember that there are cases where it may happen that one of the two is higher than 1 for some reason. Okay, so here, no, we don't have that problem. So a unilateral transistor for us here with magnitude of S11 and S22 less than 1, it's also unconditionally stable. This is very important because you don't have any more to check about stability. What does it mean that is unconditionally stable? Why is that important?
Because we don't need to determine the stability circle, stability region.
Yes, so because all of the Smith chart, it's for your use. You can use any point on the Smith chart, all right, for gamma S, and any point on the Smith chart for gamma L. Your transistor is not going to oscillate. So that is important. So we don't check. Now, do you remember what happens when a transistor is unconditionally stable? When does this transistor get the maximum available gain? When these two conditions are satisfied. When gamma S is the complex conjugate of gamma in, and gamma L is the complex conjugate of gamma out. And as a matter of fact, to remind you what I mean by that, I'm gonna add one page. Okay, so the amplifier, the transistor is here. Let's say this is your transistor at the center. Okay, and in fact, let me do this better. Okay, that's your transistor. That's the BJT that you got, BJT. And then on the front end, you have, this is connected to an input matching network. All right, and then at the output end is connected to an output matching network. Okay. So in the input matching, so here is the, on the left of the input matching network is your source. All right, and this is RS or Z sub S to be more accurate. That's how we use it here. And On the other side of the matching network is your load of the output matching network. And we assume for now that ZL and ZS are Z0, are 50 ohms. So what do we have as gamma in? Gamma in is this one. And gamma out is this one. And gamma S is this one. And gamma L is this one. Okay? So when this is unilateral and is unconditionally stable, then we say that let's assume that this one has a gain GS, this has a gain GL, and let's assume that this has a gain G0. So the total gain for this, say G, and let's assume this transducer gain or the available gain in that case, let's assume that it's going to be that we have in the front, we have a complex conjugate matching at the source and complex conjugate matching at the load. Let's assume that. So the available gain will be GS times G0 times GL. Do you remember what, let me ask you then this. Why did I make this comment about the front end and the back end, the source and the load? What is the available gain? How do we define? Also, please remember to remember the definitions for the gains, and I'm going to show you where those definitions are. Okay, it is what we call the review of LNA. If you go here, all of these definitions, all right, we have put them together and these are the equations. So the definitions. Available gain is the power available from the LNA to the power available from the source. This is the available gain, all right? And if this one, if we go now to our problem. So if the available gain is the power which is available from the amplifier is this one. That's your amplifier. So if the available gain is the power available from your amplifier towards the load, divided by the power available from the source to the amplifier, what conditions at this end, and at this end will make sure that your amplifier sends the maximum available load to the maximum available power to the load, and your source sends the maximum available power to the amplifier? What conditions will make this happen?
No reflection.
Remember what we said, the maximum available power? When I have here, let's assume that this is a load I have, and this is my source. Okay. When do I have the maximum power going from the source to this?
Conjugate matching?
Yes. No reflection is not conjugate matching. No reflection here, if you say that here, I want to have zero reflection, that implies that the input impedance here is the same with this above. That gives you zero reflection, but it does not give you maximum power. Maximum power goes to this load only when the input impedance here is the complex conjugate of this base. Now, if this base is real, obviously the two are identical. But if this base is not real, as it happens in most cases, then you have a difference. They're not identical, all right? So you always need to remember and be accurate in how you describe that. Maximum power goes under complex conjugate matching. Do you remember that? Is that clear to all of you? That's very important. Okay? So conjugate matching here will make sure that the maximum available power from the source goes into the amplifier, and conjugate matching here will make sure that the maximum available power from the amplifier goes to the load. Now, however, we introduce two more conditions here and here. It's not only that we need to have the ones outside, we need within the amplifier, we need to have conjugate matching here and conjugate matching here. And if that happens, and if therefore your gamma S is the complex conjugate of your gamma in, and your gamma L is the complex conjugate of your gamma out, then what happens to this power, available power, becomes maximum. So that becomes maximum, therefore this becomes maximum, and this becomes maximum. The one in the center remains the same. Why is that? Because if you remember, the one in the center is equal to S21 square. Okay, and now when you have, I'll erase these two. And now that you have this, you need to remember, not necessarily by heart, but you need to know that this one is going to be S11 square. This is going to be S21 square. And this is going to be 1 minus S22 square. And this one here, oops, no, hold on. And this one here, this one here is GS max. This one here is always G naught, does not change from the matching conditions, always remains that. And this one here is GL max. And now, since I have given you all the scattering parameters, you can find all of this. You can find all of this now. Any questions? And you know how to find that. I will probably ask you, say, calculate the optimum terminations for maximum gain. And I could ask you, find the maximum available gain. I could ask you as a question. And then that is the process you have to go. And as a matter of fact, even if I don't ask you for maximum gain, if you want to design an amplifier, you need to know how the maximum gain that it can provide is. Because if the maximum gain is 9 dBs, and then you try to design it for 10 dBs, it's not going to happen. You cannot get 10 dBs out of an amplifier that can only give 9 or 8. So you need to know what your maximum gain is. And if your maximum gain is 14 dBs and you try to design it for 4, then you are underutilizing the amplifier that you have, because you can give a lot more and you don't utilize it. Any questions about that? About those concepts? So all of this is here that I have, that I was telling you before. And then if you calculate, if you put the values in there, you find the GA maximum, in this particular case, is 16.45 dBs, the maximum you can get. Now, obviously, if I want to go, usually what happens, devices that can give you a lot of gain cannot necessarily give you very low noise. There is something in between these two. There is a trade-off for these people who design transistors. There is a trade-off between low noise, F minimum, and maximum gain, GA maximum. You cannot have you cannot lower very much F minimum and increase very much G max. You cannot do this at the same time. So when you have a G max that is very high, then you expect that transistor to give a modest noise, not very low, in other words. So that's what we found for this. Any questions before we go to the next?
So just to clear something up, Professor, when you say calculate the optimum terminations for maximum gain, you just mean find the optimum reflection coefficients?
Yes. And
Okay.
then if I wanted you to find the matching network, then I will be very specific about it. And I will say, and then calculate from the terminations the matching networks.
Okay, thank you.
All right. Yeah, you're welcome. So here, now I would like to do it here so you can observe what I'm doing, because I think some of you still have a problem plotting circles. So let me go back to what I'm asking in this problem. Here in this problem, I get, and I will try to do that. I will be very explicit in my questions. Step 1, I will give you in small steps. I'm going to give you many small steps that you have to do, all right, in the final. So one step, here it's a bigger steps, but I will give you small steps. For example, in this, instead of A, I could say, calculate the optimum terminations for maximum gain, and then B, I will say, calculate the maximum gain, maximum available gain. All right. And then instead of B that says, draw the constant GS circles, I would say, draw only one circle. I can ask you to draw only the GS equals so in dBs circle. All right. So I can ask you to do only one circle. I don't want to do many. But in here, I say many. And when they don't ask you for one circle, but you have to do a design, then you develop a map, develop a matrix like that. All right. So in this case, in the problem, let me again remember, you have to remember the questions, can read them carefully and remember them. It says here, draw the constant GS circles. That's what it says. What is GS? This is GS. It's the gain of the input matching network. We only know the gain when it's maximum. We know its maximum value. That's the only thing we know. All right, we don't know. It can be lower if the matching network is different. G sub S depends on how we design gamma S, how we select gamma S. So a different selection of gamma S, not this one, if we were not using this gamma S, but we choose a different gamma S, then GS will be different. For this gamma S, your GS is maximum. All right, and from the calculations we found, that GS maximum is 2.14 as a number and is 3.3 dBs if I change it from a number to dBs. That's how much comes from that matching network with the appropriate gamma S. Okay? So this, if they ask me to design the input gain circles, and since I have this one, then I know all of my Smith chart is available because it's unconditionally stable. And therefore, I'm getting these expressions, which have been available. And it's in the notes also, you know, here, if you look at these notes, then I have all of these are in there. I have put everything there for you here for input and here for output. Oops. Got that. All right. So go back to our own. Okay. So the input gain circles. Then what do? I go and create this matrix. Now, first of all, GS, observe GS. GS here, which is this, is small GS rather. Small GS is the ratio of the gain of your input matching network divided by the maximum gain they can get. And of course, both GS and GS max in that ratio, they are not in dBs. I don't want you to go and calculate a ratio when you have dBs in there. I have seen that. Some of you are doing this. You know how bad it is to do that? Because it implies you don't know how we get dBs out. You don't get ratios of two entities, quantities with dBs in there. All right? So if you want to get the ratio of G sub S, G small sub S, you have to convert GS maximum into a number, which I have in fact calculated here. The GS maximum as a number is this one. So the maximum value that GS can get in a number is this. Now, of course, in dBs, we always translate it in dBs because even if the ratio needs the number, we design using dBs in our mind, all right? That's what we have here in our brain. We think dBs, but we write numbers. So what we need to do is to make that conversion from dBs to numbers or numbers to dBs, whatever. You need to make sure that we are careful. Here, the ratio is on numbers only. Then, when small gs is 1, that means that your capital G sub S has the maximum value, which is 2.14 as a number. If GS is 1, then what happens to GS? GS becomes capital, becomes GS max. What happens to C sub S? C sub S becomes S11 complex conjugate, all right, here. And therefore, since C sub S is given by this expression, all of the values of C sub S, which are complex values, will have the same phase, which is the complex conjugate of S11, and S11 is this, so it becomes minus 175, all right, here, and then has different magnitudes. The highest magnitude is 0.73, and then it goes down from there. Now, 1 goes to 0.75, 0.59, 0.47, 0.37, and so forth. And the values for GS go below 2.14 until they go below 1. So in dBs below 1 is negative. That's why you see -1 here. All right. And then you get the values of CS, and then you get the values of RS. Now, let's assume that I want to design the GS in dBs equal to 2 dBs. So which of these columns will I pay attention to? I will pay attention to this column.
So, Dr. Katehi, so we just simply assume GS by ourselves, right, in dBs?
What do you mean? Could you explain?
We find, do we calculate GS in dB, or like we just assume one in dB?
You're talking about this here.
Yeah.
Yeah. So here, since I say calculate the circles, I did not ask you in the final. I will tell you which circle to calculate.
Okay.
All right. Here, though, since nobody has told me which circles to calculate, I create a range. I go 3.3 dBs, 2 dBs, 1, 0, -1. All right. But in your final, and usually that's what we do in design, we put many circles. But in the final, I'm going to tell you which circle to design. So you will not have to do a whole matrix. Okay?
So in the final, if we calculate GS max, you might say find the input circle for GS dB equals 1, and then we're supposed to find all the remaining numbers?
No. In the final, I will tell you, find the GS max, and then I will tell you also plot the circle GS equals so and so. Or I may do it for the back end. Instead of GS, I may go to GL. Okay? But I will tell you, plot the circle. I would tell you in this case, plot the circle that corresponds to GS 2 dBs, equal to 2 dBs. So you will only have to calculate this row, the front one. Did I respond to your question?
Yeah, that's exactly what I was wondering about.
Okay.
Thank you.
Okay. All right. Now, who is going to tell me how I'm going to plot this? Who is going to tell me how I'm going to do that?
We find the angle using the outer ring, and then we draw the line there, and then we find the distance on the line using CS, and then and then from that point on the line from CS, we draw a circle with the radius RS, and we get the radius RS by using the scale at the bottom.
Yeah, let's go one step at a time. Thank you, though. I mean, the whole description was correct. So, but let's do the first one you said is to find the angle, -175. And you remember, these are reflection coefficients we're looking at, all right? So which ring of all of those you're gonna start looking at? You are gonna start looking at the ring that says angle of reflection coefficient. You see that? Not the lower ring, because all of these that we are looking are gamma. All of the values we are having are reflection coefficients. So you're looking at that ring. So then you will go around here until you hit -175. Is someone there? Well, anyways, I'm gonna erase that because. So you found that, maybe I'll keep this one. I'll keep this one so you remember. So then -175 is somewhere here. -175 is here. And then I'm doing this. Okay, and we'll move it accordingly. All right. Somewhere there, okay? That is minus 175. All the centers of these circles are on this line. Okay, now all of the centers, all of this, so all of this, the line here, I will put here, all of these centers are on the same line, which corresponds to minus 175, okay? But I'm gonna do only one, the 2 dB. So I will do the center has a magnitude here of 0.629. How do I find 0.629? I go here on this that says reflection coefficient. You see that? I go to the one that says reflection coefficient. Oops. There. And then I measure from here to 0.629, we said. Something like that. Let me do it better. 0.6, somewhere there. Okay, I mean approximately now. It's not exactly. And then put it a little further. And then I'm gonna draw from there a line vertical. And this line, so it does not mix up, do it like that. And there I'm gonna write a circle that goes from this point here. The circle will go, it will have a center at the center of the Smith chart, and then it's gonna go through this point here. Here. Oh.
What is the C you choose? The magnitude?
Wait.
Okay.
Let me. Okay, I lost the whole thing. All right, tell me. It was my mistake. What is this again? You're
The
asking me?
magnitude you chose for the center.
Yes.
We calculated. What is it? The number?
0.629.
Okay.
It was in the, yeah, the number you wanted. Okay. Okay, so here now what I was trying to do is to go and write a circle like this. Wrong. This one. There. Something like this. So then I'm looking where this circle intersects the minus 175 line, and I find this point.
Well, for the circle of radius, for the C, we should use the intersection of the magnitude vertical line and the phasor line as the center.
No, the vertical. It happens here because minus 175 is very close to 180, to minus 180, that it seems like it's the intersection of the vertical line and the minus 175, but it is the intersection between the radius of, between the circle, this circle here, and the minus 175. Because if this line, the minus 175, were to be different, if the line here were to be here or here, where would your center be?
Just, oh wait, it should be at the other side, like to measure the length, the physical length from the center to the 0.62 something on the reflection coefficient, and then to find the equivalent point on the right side of the center, and then draw the vertical line and to find the intersection.
Intersection between what? Let's assume that this is
Between the vertical line and the Fraser angle.
That's wrong. That's not right. Let's assume that this angle here was minus 55, okay? So I find minus 55. Then what you said, which I know if I understood well, you said that we would extend this. And
no,
then
it's to measure the length from the center to the 0.62 something, 0.63 on the left hand side, and then find the point with the same length on the right hand side of the same axis.
on this axis, on this one.
No, on the reflection coefficient axis.
Well, I found that. Is that where you're talking about this one?
Yeah, and then move that line to the right hand side
Why?
to find the center.
Okay, let's assume that I move it. I'll move it to see, I move it here.
Yes, and then
What?
the intersect, yeah, and then draw a vertical line on the right hand side, on the rightmost, yeah.
And
And
then
then the intersection between the two lines, between
where? Here?
the angle of negative 55 degrees and that vertical line is the center.
Here?
Yeah,
It's wrong.
that's what I think.
Total, no, it's wrong. And if you do that, then you're going to get a very wrong result.
Then the correct one should be just the 1.0 plus J naught is the center.
So how you're going to find it? You draw this vertical line here, which I'm going to change the color right now so you don't get confused. Let's make it this purple. You're going to draw the circle that goes through this purple line, purple. And then you will find where this circle, if the angle were to be minus 55, I will make it also purple. All right. Then your center is here. That's the center of your gain circle. There's a big difference between the two.
What about the radius?
What radius? That's a different story. I'm talking about CS right now.
So the actual circle doesn't, the origin of the circle is not the center of the circle.
What center of the circle?
The actual center of the circle is just the center of the Smith chart of this circle, the purple circle.
That is this purple circle that you say, which I'm just showing you right now. This purple circle is the circle of constant VSWR on a line, means all the points on this circle have the same reflection coefficient, magnitude. So C sub S does indicate a reflection coefficient. And C sub S has a magnitude, which we found here to be that. And then from here, also, I'll change them back to the initial color for our problem to be this. Just happened to be close to that. I cannot move it closer. And This one, it's the constant VSWR circle. And maybe I can move that a little closer here. And then this goes to minus 75. And I will make it also that. And now the center, our center is this one.
Yeah. Oh, I understand. So that circle is the constant VSWR circle, not the gain circle.
No, that's a constant VSWR circle. I have not done the gain circle yet. Okay, so now that I found C sub S, which is here, now that I'm going to find R sub S, which is 0.274. 0.274. I'm measuring now 0.274. I'll use a different color. 0.274, which is somewhere here. And then I'm going to take this. I'm going to take it here and I'm going to draw a circle. That's the best I can do here. Draw a circle that can go through this point with the center to BCS. And that circle has to be that one close to. Now, that where this is the radius, that is your GS to the B circle. Okay.
So Professor, the radius of that red circle is the RS value from the table above?
Yes. Yeah.
Okay.
I took it. Yeah, exactly. I mean, if I copy, duplicate, say, not this one, sorry. Cut.
And did you measure it on the scale below?
Yes.
Okay.
Let me see. There. If I duplicate that and I take it down here, yeah, I measured it. It's like 2 point something. It's not exactly. Yeah. So that's your G sub S equals to dB. Any questions about how we have some late comers today? Let me see. Okay. Any questions so far? Is that now clear how we get these circles?
It is clear, but I have a question.
What is the question?
For output matching network gain, we also do the same procedure, right?
Yes, exactly.
And
But the equations are different, the process, but these ones are different.
yeah, of course.
Yeah.
And then we find the mutual area between the gamma S and gamma L circles with the noise.
No, oh, the noise, no. With the noise, you only do the GS. You remember what I said, the noise?
Oh, I see.
The
So
noise
yeah,
only impacts the input matching network.
because it is unilateral.
It does not matter. Noise, whether it's unilateral or not, will only intersect with the input matching network.
Okay.
Because the noise is written in terms of gamma S.
Oh yeah.
All right. There is no gamma L in the noise.
All right. Then we find the gamma L from the output matching network circle anywhere inside that circle.
Yeah, in this particular, so you're talking about the unilateral case.
Yeah.
In the unilateral case, because the output matching network and the input matching network do not interact, So you design the output matching network for maximum power, which is the complex conjugate matching.
Okay. So
Always.
it's just one.
Do you understand that?
I think so. Yeah. Is it just 1 point? Is that right?
Yeah, it's 1 point. There's no circle.
Okay.
Because the complex conjugate matching, it implies here, it implies this. And since you know S to 2, then you know your gamma L.
Mhm.
So you can design immediately your output matching network. And that is going to give you maximum power in the output matching network.
Oh, I see.
So what we are negotiating is this if there is noise. If you don't worry about noise, then you design it for maximum available power, which is this. If you only care about maximum available power, if you're going to design an amplifier to give you the maximum power without worrying about noise, then you do that, which means you know exactly what your gamma S is and what your gamma L is. I mean, there are 2 points only, all right?
Mhm.
And they're given because S11 is given, S22 is given. So then from gamma S and gamma L, you design the matching network.
Okay. Okay.
So that's what you do.
And even okay. What about if we have like output VSWR, the VSWR out? Still, we don't.
That's deep. Well, you have a VSWR out, then you have to design it for the
Okay.
output. But we're not going to have this in the final. Remember what I told you? I'm not going to give you a VSWR.
Okay.
It's complex. It requires a lot of time, and you're not going to have the time to do it.
All
But
right.
just for your own information, if you have a condition, a design spec that says that I want a VSWR at the output port, all right, to
Mhm.
be less than, so for example, it will tell you that you need a VSWR at gamma L, or at zeta bell, excuse me.
Mhm.
It will tell you that I want my VSWR at zeta bell not to be less than, to be something very specific or less than something, all right? Because the load, we design for a load which is 50 ohms, practically. But most of the time, the load is not 50 ohms. It's something different. And people will come and tell you that I want for a given load, my VSWR, whatever load they give you, I want my VSWR to be less than 1.2, for example. In that case, then you will have to do the VSWR circles and then select gamma L separately.
I see.
But we don't do this we're not gonna have to deal with this. The only thing that I may ask you to do in the final is to design for a gain and noise, which we're gonna do next.
Okay. Thank you.
But if you design for gain and noise, you only do the input matching network. Is that clear? Because
Yes.
noise impacts only the input matching network.
Yeah. It's
Okay.
clear. Thank you.
Okay. All right. Any questions before we move on? So now we have the GS equals 2 dBs. Then you can put other ones, but I told you for now we are going to do this. And then what we're going to do next, in this one, I said do all of the circles. If you were to do the other circles, you will do the same thing, and then you're going to have many more circles, all right? But I don't want you to do this now. So, and I'm not going to ask you for too many circles in the final, but I would like you to know how to do them because I'm going to ask you for one, and this one you have to do it correctly. Now, I say calculate the optimum terminations of, see, that's another thing. I ask you now, look at C, to calculate the optimum terminations for minimum noise. Let's think about that, okay? And first of all, let us think, let's go and get the expressions for noise, first of all, before we do anything else. So here it's section C. Let's do this, C. Okay, so find terminations for optimum noise. Okay, I'll bring the equations for noise, but I want you to think in the meantime how we are gonna find the terminations for optimum noise. So while I'm trying to transfer the equations, I want you to think about it. So take a few minutes to think about it. Okay. It says two things. Let me move them a little further down, this one, so I can bring to remind you of something. And I'm here. What I want to do is bring this one here. Okay. All right. Do you remember what I said about noise? What did I say about noise? That noise impacts what?
Just the source matching network.
Exactly. Why is that? Because of this. You see how noise is impacted by what? By gamma S only. Everything else is given. F minimum is given from the transistor. Gamma optimum is given from the transistor. R sub n, which is the ratio of the resistor over the reference impedance, is given. The only thing that is not given in this expression here is gamma sub S. All right? So a choice of gamma sub S has the possibility of giving us a noise that is very specific in value. Okay, so obviously a gamma sub S is going to give us a particular noise, which means that I have to select my gamma sub S on the basis of the noise I'm going to generate. Now, if my gamma sub S choice is determined by noise, what about the gamma sub L in this unilateral transistor? How am I going to find gamma sub L?
We just conjugate match with R out, and since in our case it's all unilateral, it's
Exactly. You remember what we said? In a unilateral amplifier, the input matching network and the output matching network don't see each other. So since whatever I do on the input matching network for noise is not going to impact the output matching network, of course I would like to get the maximum gain out of it. And the maximum gain of the output matching network comes out of what? gamma L equals gamma out complex conjugate. So I'm going to have this for unilateral, all right? So let me move this higher and write here unilateral. So you don't, you know it's unilateral case. And so this applies for any value of gamma S. But the value for gamma S needs to be specified by the noise. Okay, and so here, if I remove that for a moment, what do we know about noise? First of all, the problem says find terminations for optimum noise. Optimum noise means minimum noise. Okay, so we found the output termination for this. We just talked about it. So the only thing is that I want to find now this. And I want to find this so my noise is minimum. So out of this equation, what do you think gamma sub S should be?
Gamma suboptimal.
Yes. So from here, that implies that gamma sub S should be gamma optimum. How much is that? I have given this in the problem. Oops, not this problem, this one. So gamma optimum is 0.5170. 0.5170. Okay, so, sorry, I'm going down here and I want, so in this case, I say I solve the problem practically by saying, let me move down this one a little further. So now, since I know gamma optimum, in this particular case, I will have that gamma S should be gamma optimum. And now I found gamma S, I found gamma out, gamma L, and now I'm done practically for this problem, for C. Okay, do you have any questions about that? Do you have any questions about how I calculated it?
So gamma S equals gamma optimum, right?
Why? Where did I get this value?
It's just what you have written.
Why? Though I wrote that.
I
How
don't
do I?
know.
You don't know, look at the question here. Look at this relation.
Termination for optimal noise.
Yes. If your noise becomes optimum, which is F minimum, when this one goes to 0. When does this one go to 0?
Gamma S equals to gamma optimum.
Exactly. See, that's where I got this one from.
Okay.
So this one here comes from there. Okay, because I want this to be 0. I want this one here to be equal to 0. Okay. So this one is 0.5, 170. And that's it. So now I have gamma S. Any other questions before we move on? Now, let me tell you this. If I give you gamma S and gamma L, how much is gamma L here, we said?
S22 conjugate.
Exactly. Let me see. Okay. If I give you gamma L and gamma S, do you know how to find the matching networks? Would you know how to find them?
Yes.
Is there anybody who is not sure? Because I may ask you, depends on what questions I'm giving you. All right, how many? If I give you
Yeah,
many.
I would like you to go over it again.
Okay, we'll do that a little later after I'm finishing. All right, so we'll do it at the end. Okay, so we found that. We'll see how to do a matching network. Then, what else does it say here in this problem? One of these questions may be find a matching network. Now it says design. You see, I say input and output matching network. Okay, so now I want you to design them, the input and output matching networks. All right, for this C. So now we are going right there. Perfect. So let me copy this one. Copy to go it a little further down. We don't even have to do the circles. This one, however, do you know how to do circles if I ask you? For noise?
Yes.
You need, is the same like any other circle you do, all right? But you have different equations. That's all to it. All right. So let's now find the matching networks, which is, I will erase that, this.
For the noise circles, it's the same procedure as the gain circles, correct?
Exactly. All of the circles have the same, the stability circles, the gain circles, the noise circles, the same process. Different equations, obviously. But how you, after you find the value for the center and the radius, the process is the same. So now let's do the input matching network. Input matching network says here for input. So put them down. So here we'll do input matching network, and the output is going to be exactly identical in the process. Now, what do we know? That we have to make gamma S to be 0.5, 170. That's gamma S. That's 1 point. How do we find this point? We go here and measure half, 0.5, on the reflection coefficient scale. We go and measure 0.5. It's from here, there. Okay. Then we want to still find this point. The process is the same, finding reflection coefficients. We still then draw a line that goes here. No, sorry. Draw a line. Goes there. And now, let me make this line here to be dotted. And then I will write the circle that goes through the center of the Smith chart, which is here. I draw the constant VSWR circle that goes through like here. Okay. Approximately. Okay. Like that. And then what else do I do? What is the phase 170? How do I measure 170?
Just on the circle of reflection coefficient angle.
Yes.
Just look for 170 on the second,
yes.
second outmost ring, a third outmost ring, sorry, of the
this one. Exactly.
We
So
don't
we go
actually to go over the whole circle. We just look at the third inside most ring.
Yeah. Right.
The third outside most. Yeah.
So we go there. It's right here. we write a line. Right? Then we do it like this. And then we find the place where the circle intersects. Okay, there. We find a place where the circle intersects the line, the solid line, and it's this one. Okay, that is the point. That is the gamma S. All right, point. Now, where do I need to go with the match? I'm in the matching network. How does the matching network look like? The input matching network. It looks like this. My input matching network is this one. Here I have a 50 ohm. And then this is where I am. And now I'm gonna design this so that my input here, reflection coefficient gamma S, is this point here. That's my gamma S, all right? When I look at the reflection coefficient, what do I do with the source? What do I do with the voltage source?
You short it.
Yes, why is that?
It has to do with the Thevenin equivalent.
Yes, so practically when I design gamma S, I'm looking for the input impedance here. Do you agree? If this is what I'm looking for, if I can design a matching network with this input impedance, then practically I have my gamma S. Do you agree? Where now gamma S will be Z input S minus Z naught over Z input S plus Z naught. Do you agree? So practically, if I design a matching network with this input impedance, then I'm done. But when we design a matching network for an equivalent input impedance, that's the equivalent Thevenin. So all of the voltage sources become 0. All right. So practically, what I'm looking here to do is to design this matching network. So when it is terminated at 50 ohms, as this one is, I see here in front this impedance, Z in S. That's what I want to do. Do you agree with that statement?
Yes.
Okay. Now, if I want to be on the Smith chart for impedances, what do? I normalize everything. And if I normalize, Z naught becomes 1. Okay, and of course, 50 becomes 1 if I normalize everything. And that becomes 1. And that's it, this one. And what is this impedance? Where is this impedance here on the Smith chart? Show me the point of this impedance on the Smith chart.
Just to solve this problem, to solve that.
Show me on the Smith chart this impedance here.
It just be gamma S.
Yes, yes. Yes, this impedance, because of gamma S is the reflection coefficient that this impedance creates. And we know that is here. So on the Smith chart, that point here also represents Z in S, normalized. That's where my impedance is located here. It's just that I measure it. I don't look at the red circle where I found gamma S. I look at the resistive circles and the reactive circles on the Smith chart. So what is the value of this if you were to read it? Let's do that just to practice a little bit. Tell me the value of this one. Approximately.
I can't really see, but is it point
Yeah.
3.4? Oh, okay.
Yeah, it's point, say 34. All right, the resistive part is 0.34. And the reactive part?
It's plus J 0.08, I think.
Maybe, let me see, 2, 4, 6, 7, 9, approximately. Okay, so it's a plus J 0.9, 0.09, excuse me, 0.9. Okay, do you agree with that? The others, the rest of you, do you agree with this? Would you get this value if you were to read it?
Yes. Yeah.
Okay, good. So now, where do I want to go? Where is on the Smith chart this destination? That's my destination. So I'm here, and I'm going this way. All right, so I'm walking. It's like this little guy here and goes. I start from this point here and I want to go. Where I want to go until I see this point. Where is this point here?
Center of the Smith chart.
Yes. That point here is this one. I want to go there. How am I going to go there?
Move with the circle to the unity circle.
Before I do that, what kind of decision should I make?
That if you want a series or a shunt.
Yes, if I want to use a series or a shunt stub. Now we know that we cannot arrive at the center of the Smith chart if we use transmission lines without using a stub. Because the stub is the only way of getting down to the center. All right? We can move around the circle forever. I mean, you can move around the circle forever if you are on a transmission line. You can go circles, multiples, millions, but you will never be able to get to the center of the chart, which means to have an impedance of 1 normalized, unless you go down one of these lines. And specifically this one, because that is what goes towards the center of the Smith chart. No other line will get me to the center. So this one down here implies a stub. And if I want to put a series stub, then I'll stay with impedances. But if I want to put a shunt stub, I may tell you to use a shunt or a series, all right? I may be very specific and say, develop a matching network with a shunt or a series stub. Let's assume that I want a shunt stub. What are you gonna do?
Work with admittance.
Yes, how are you gonna go from an impedance to an admittance?
180 degree in the opposite side.
Yes, so Did you hear that, everybody else? To go from Z and instead using a Smith chart for impedances, to convert the Smith chart to admittances, I extend this line until it goes to the other side of the Smith chart. And this point here, now I will do green. That's an admittance. And that's the input admittance here. All right. So in this case, I will not use impedances, normalized impedances. I will erase that. And I will use a normalized admittance. But this still remains 1. All right, because when I normalize admittances, I normalize with a characteristic admittance. So a 50 ohm impedance is 1/50 in admittance, and I will normalize with 1/50. So it gives me always 1. All right. So I'm starting with at this point that I call A. And now I have to move until I go to point C. My point A is here. And my point C is, what color should I use? Red. My point C is here. I'm gonna go from A to C. How am I gonna go? I have 2 ways of going on the circle. I can go left or I can go right from where I am. Which direction am I gonna take?
We're gonna move towards the load, so counterclockwise.
Yes. So I go here this way. You see that? It says wavelength toward load. So since I'm going towards the load, the only way I can go is like this. I can go only this way. So I'm gonna keep going from here.
So
until,
Professor, why toward the load, not to the generator?
where is your generator?
Isn't this the source match network?
The generator is behind you. It's here. You don't have, we removed that. So where is the generator? The only way the generator is behind you. If you're here, the generator is somewhere here now. Your load is this, is 1.
So it's always towards the load for all the matchings.
Not always. For example, if I were here, and then so there are times when I ask you, what do I ask you? To, okay, so let's assume that you have the following problem. As a parenthesis now, let's assume that you here, I have a load, and now I am moving away from the load. I keep looking here and I wanna put somewhere a stub here and so forth, but I'm moving like this, away from it. In that case, I'm going towards the source. If I move backwards, all right? So I'm starting here, but then I wanna move to the source, then I'm saying, and when does this happen? That happens if I have a lot of information about the load, And I don't necessarily know that much here, but I want to find in every location, for example, somebody comes and says, I have this load here, which is ZL, and I want you to place something here. So I see a 0 reflection coefficient here. The best way in this one is to start moving along a line and find the right place for you to put a stub, but you do that, you move towards the source as you are going further away. But don't worry about that for this one. So you remember, when we do these matching networks, you always move towards the load in this case. But it's not always true that for all matching networks, you move towards the load. So you always have to ask, you always have to ask yourself, which direction am I going? All right. You're always in this problem here. Your desire is to move to the load, which is at the center. This load is at the center, but this load is not at the center. So when you have a load which is not at the center, you move away from this until you always go to the center. So on the Smith chart, your goal is to always go to the center. If you go to the center and you move towards your load to see that, then you have to move into the right location. If to go to the center of the Smith chart, you have to move away from your load, then you move to the opposite direction. But you always have your last destination. Your last destination in a matching problem is the center of the Smith chart. Do you remember that?
Yes, but I have a question.
Yes.
So instead of the shot, if we were using a series, don't we go the opposite direction?
Yes. You will always have to go, not the opposite direction. You will go always towards the load, but you will start at Z, not at Y. You always have to follow the same direction. Why did you think that you have to go to the opposite direction?
I think I saw some, I mean, in your examples on your notes.
Where? I never do that. I don't change direction if I go from Y to Z.
So if you're using a series stub, you just stick with the Z, right? So you would go from Z to that same point?
But yes, you start from Z, but the direction remains the same.
Right. So the length would just increase.
Yeah, exactly.
Okay.
So now I go to point B, from A, I go to point B, which is this point. And then from there, I go down here to go to the center of the chart, where is my destination. So what does that really mean in terms of my matching network? That means that I start from A and I go to B. And since I'm going like that, what does that make me do on the matching network? What does it mean that I'm going along the red circle?
Transmission line?
Yes. When I start at Y, this is my point A prime, transmission line, all right? When I move on a transmission line, I go on the constant VSWR circle, so which is the red one. So from A prime to go to B, which is here, I go on a transmission line. This is my transmission line. And I move by a distance from A to B. And then what do I do at B to go to C? Remember, C is here. That's my load, which is normalized 1. That's the center of the Smith chart. This is the center of the Smith chart. That's point C. What do I do to go to point C from B? Can I just go? What do I add?
You'll need to add a stub there.
What kind of stub?
Usually it's an open circuit stub.
We don't know yet.
Oh.
What kind of stub is it? Since I'm working with admittances.
Oh, it'll be a shunt stub.
Yes, exactly. So I'm putting here a stub. All right. And that's what allows me to go from B to C. That's the stub here. And that's what happens by going from here, from B to C. All right, now how do I use these distances from A to B and from B to C? Why do I need them? To give me the length of the distance for the green on the transmission line. So the green arrows, the total of these, will give me the distance on the transmission line. The purple arrows will give me the length of the stub. All right. How do I find the distance on the transmission line? I extend this line further, and then I draw a similar line. Okay. And here I will have to measure, there is only one really, there is only one circle where I measure distances, and it's this one. So I have to move from A to B. I have to go a distance. It does not matter which way you measure them. Is you always subtract from the highest the lowest. So the highest here number is 0.266, always in lambda. And the lowest here is 0.168. So the distance on the transmission line, this distance here, is the difference between 0.266 minus 0.168 lambda. And that gives 8.9 lambda. So I have to move along this by 0.098 lambda. Okay, now we have to find the length of the stub. The stub is the purple, we said. Okay, so practically for the stub, I have to look at the purple from here, from not here, excuse me, this one. The stub goes from here, here. So the stub will go from here. And now where am I going to stop? This is the question. Before I stop, I have to ask myself what kind of a termination I need to have at the stub. An open or a short? If I have an open, I have to stop at a point where the admittance is, how much is the admittance at an open? Open circuit, how much is the admittance of an open circuit?
0.
0. So 0 is here, and therefore this point here will be open. Open, shunt, stub. And what is going to be here? Shorted shunt stub. So if I stop here, all right, so I move from this point, which is 0.1339 lambda, to this point, which is 0 lambda. So the stub is going to be 0.139 lambda. And that's the length of an open shunt stub. And that's the equivalent, the matching network. Any questions?
I do have a question.
I still don't understand why it's moving towards the load instead of towards the generator for input matching network.
What is the center of the Smith chart?
The center of the Smith chart, it's 1.
Okay, is that at the center? Is that the load or the source?
1 is the load.
Well, 1 is the load. So at the center of the Smith chart is your load. So as you walk towards the center of the Smith chart, which direction do you go?
Load.
Okay, that's it. You answered the question.
Professor,
Yes.
could you open one of the review document you posted, the one with the 22 pages?
Tell me, what is the title?
We solved a LNA that is not unilateral.
Review on LNA or example of a design of LNA? Which of the two?
Need to review example of a design of an LNA
With corrections. Okay.
Yes.
All right, so here, tell me.
Would you go down to designing the matching network Smith chart? Not this one, the page 17. Yeah, this one. So in this case, you you move toward the generator. From
Let me see. I moved towards the generator. You are right.
I mean, I think because the other one we used with shunt, this one is series. Is it the reason, or?
No, I think so. I wanted to go practically here. I needed to move in this one. You're right. I needed to move towards the load because every time the load is at the center. So for this one, let me see. I would need, even if it's an impedance and it's a series stub, I needed to move towards the load and not towards the generator. So it was an oversight. And for that reason, I will have to correct it. Obviously, we'll do it here. Oops, what happened? Can you see it? Okay. All right, so I will have to remove all of this. I don't know what I was thinking when I did that, but thank you for reminding me.
So for this one, you should use moving towards the load.
Exactly. Absolutely. I would have failed the final. Seriously, had I done that.
Dr. Katie,
Yes.
so what situation would we move towards the source?
Yes, I'll tell you. I'll show you. Let me fix this for a moment.
Okay.
I just need to do it right. So I had yellow, green, all right. So. I mean, even I show that here for some reason. Okay. Let me see. Not do it. Okay. Okay. So that's what you have to do this year, to find L and to find, so obviously for, what do I have? To go from here, there. You have to do that. And your B is down there. Here. And so I'll do this one. Okay, so then you measure and you move towards the load. So in this case, you will have to move. All right, so let me correct this for a moment. This one.
Also, there is another example that you.
I did the same?
Yes.
Okay, is it on the same or another one?
Another, this one is on the lecture.
Is it in the same one? Same?
Not same document, it's a different document.
Okay, I will find out. I will. Okay, this one I have towards the load. Okay, I will, tell me what other document is it, I will take care of it.
It's on November 6th, lecture and example of LNA.
Example of an LNA?
Yes, on November 6th.
Okay, so an example.
Finally, are you going to post the recording and notes?
Yes.
Oh, okay.
The notes yesterday. So let me see. This one, review of an LNA.
No, it has it like 4 plot for each S11, S22, S33. I mean S2, S12, S21. It started with that 3 plots at the top.
This one.
Would you go up? Yes.
Okay. All right, in this particular case, what I think I've done, so you can do the same problem from moving away from here or moving towards, but you will have to be careful when you do, it's not, so you have to be careful on when you do it the opposite direction. So for example, in this case, where is it? Z in CC is here. And then I add it, I move away and I add it. So in this case, I did the opposite, all right? So I moved away and I put the stub and I went to Z input BB prime. And then from there, I moved towards the source, towards the generator. And then I went to Z input AA prime. Is not wrong the way I did it, because I used this equation and the result is correct. Because of the way I moved from, in this one, the way I solved it is by going from the center. I solved the problem going from the center towards the input impedance, which is the source. So the source is at the input impedance. But I should have for that input impedance, since I would move towards the generator all the time. So I moved from here and then I moved up here, but then I should have moved all the way around it. I look at this to see what I've done. All right, practically.
Okay.
And then, because I have to check it out in this particular case. Thank you for letting me know. But I try to do the opposite in this case. But in any case, for this one right now, to just simplify things, when we do the review, let me see. In this case, where I have that, to simplify things, you would always go, you will always look, you will remove the source, and you will go from where you are towards the center of the Smith chart. And so as you go through towards the load, you go, and then you find your first point, B, as you move towards the load, because your load is at the center of the Smith chart, and you are moving from A to B, and then you add the stub, and then you go to the center of the chart. Now, you could argue that no matter how I go, I should find the same result, which is true. But, and then I will, so you find the same result. Yeah, I mean, for the same reason, I could move from C and go towards out and towards the source to be able to find the same result that I had before. Now, I also have to tell you that on the Smith chart, because a full movement around the Smith chart is half a wavelength, the result from moving from A to B and the result from moving from A to electrically, from A, the opposite direction to B, electrically, even the length may be different, electrically you have the same result in terms of matching. So there are multiple, the reason for that is because there are multiple solutions to one matching problem. And all of them will be right electrically, will be correct. They will give you the same matching. The difference is that some may give you longer lengths than others. All right, do you understand that? That's why it's not necessarily necessarily bad, I mean, to move into the other direction. It will still, if you stop in the same position, and if you stop, and then if you do your equations correctly, your matching is going to be correct. The difference between the various solutions in some solutions have different lengths than others. That's why moving in one direction or another, it's a good thing in practice to always keep in mind which direction you're moving. So on the same chart, you don't mix directions. That will be a mistake. But you can, if you were to go into the opposite direction, as long as you stay consistent, your matching solution is going to be correct, but the lengths will be different. So you're going to have a different matching network, but it's not necessarily going to be wrong. It's going to give you the same reflection coefficient. Did you understand that? So the other solutions, the matching was correct the way we did it. It's just that in the other way that I did it, we got a different matching network, but the matching conditions were done accurately. Do you understand what is the challenge with the Smith chart?
Yeah.
There are multiple solutions, all right? And all of them are correct in terms of matching.
So,
But yes, go ahead. Tell me.
for the final tomorrow, if we had this exact problem and we moved
Yes.
towards the source and
Yeah.
did all the math right and got a matching network, would that be considered a correct answer?
Yes. So yeah, if you get me any of the matching networks, because there are multiples, all right, you will get the correct answer. You will get we will get we'll check. We'll get the accurate. I'll consider it accurate.
Okay, thank you.
If it's any of the possible matching, I will consider it accurate, as long as the matching condition is satisfied. Because that's exactly the case, that there are multiple solutions to the problem. It's not only one.
I have one more
Now,
question.
yes.
So for finding this top length, you started from 0.139 lambda, the purple.
Yes.
Yeah. I always thought we should start at like 0.168. Is that wrong?
Where is 0.168? No, yeah, it's wrong.
Okay.
Because you have to start at the point where you get the reactance. And the reactance, the point B here, and all the points on this circle have the same reactance. And the reactance is here, this value.
Okay. Right.
Okay. A stub is only reactive. It does not have a real value.
Yeah.
So to be able to find the length of the stub, you need to move here this way.
So we can stop at open circuit, or we can
Stop at short. Yes. It depends if you are impedance or admittance. Okay. It depends if you are impedance or admittance. Because for an impedance, on the left it's short and on the right is open.
Yeah.
Okay, I will post this. So the most critical thing is to remain consistent with the way you go and do this for the final. But if any, give me a right matching network and I will accept it, all right? Because there are multiple solutions, obviously.
For output matching network, we also need to do the same procedure. Find
Yes, 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 exactly.
Dr. Katei, I have a question.
Sure.
How come whenever you were doing the noise circle and the gain circle, how come you didn't have to find where they intersect to get the gamma S?
In this particular case, in the problem, I did not have to do that because I said that I wanted to find gamma S for minimum noise.
Okay.
And minimum noise you get minimum noise from here when gamma S is gamma optimum, it's just 1 point.
Okay, so you'd probably end up with a lower gain in this problem.
Yes, of course. Yeah. But at least
Wait, I'm sorry. I think I wasn't able to hear your audio.
I can now still hear you.
can you hear me now?
Yes.
Okay. I don't know what happened. The other one. Okay. Any other questions? How long was it that you could not hear me?
Just for a few seconds.
Okay.
I have another quick question. So
Yes.
sometimes you use the GP circle for gain.
Yes. That so not for the final, but when you don't have a unilateral transistor and your input and output matching networks see each other, you cannot design them in isolation. So the best way for that case is to use the GP circles.
Okay, that makes
But
sense.
we are not going to do that for the final, though. So in the final, you're going to have a unilateral transistor.
Okay, thank you.
Sure. Any other questions? Okay, so I will put this up. The recording takes a little time to get done, but I will put my notes first. And then I will, the recording by tomorrow morning, the latest.
Thank you.
You're welcome. All right, thank you all.
Thank you.
Thanks, bye-bye. Bye.